హాయ్ ఫ్రెండ్స్, ఈరోజు మనం ఈ వెలాసిటీ డయాగ్రామ్ నుంచి ఎఫిషియన్సీ ఎలా కనుక్కోవాలని చూద్దాం. బ్లేడ్ ఎఫిషియన్సీ, స్టేజ్ ఎఫిషియన్సీ, అలాగే వర్క్ డన్. ఓకే, అండ్ నౌ we go for first thing, tangential force on blade. Now I'm going to first one is tangential force on a blade, that is equal to Fu is equal to m velocity exist velocity, inlet velocity minus exist velocity is equal to tangential force. Okay, m is coming from here, mass flow rate. Okay, now I can write here mass flow rate into change in velocity in tangential direction. So then Fu is equal to m into change in velocity. This is our diagram. So this is the change in velocity. Okay, now Vw1 minus Vw2. Okay, we think here is 1 minute. Here to here is the real velocity 1. Is it right? Okay, and then look at here, B2F is the real velocity 2. B2F. Okay, B2F is the real velocity 2. And then now here we are going to know about the wheel velocity. Change in velocity is equal to real velocity 2 minus real velocity 1 minus real velocity 2. Okay, is it right? Yes. Okay, then here here is the total is coming from real velocity. Okay, yes, is it right? And now here we need to find this one. Okay, so the change in velocity is here is the same, so no problem. So now look at the here, we are going to solve this. And now we are going to power developed in blade. So power developed is equal to mu blade velocity into change in real velocity. Now here we go to write down this blade efficiency or diagram efficiency. Blade efficiency or diagram efficiency or utilization factor. Utilization factor is given by this is equal to 1 plus 2, and now here we go to now about VB and half 20 V1 square. Okay, so this is the here is divided by. So this is the general equation of efficiency of the blade. So now here I put roll velocity plus, right? Because we see here is the wrong statement. I think change in velocity is equal to VW1 plus VW2. Okay. Now here we are going to write down this efficiency is equal to change will M divided by M V1 square divided by 2. So this is coming from work done divided by kinetic energy supplied. Okay, kinetic energy supplied. Then the efficiency of blade is equal to roll velocity divided by V1 square. 2u change in velocity divided by V1 square. Now we are going to know about stage efficiency is equal to work done by the rotor divided by isentropic enthalpy drop. Okay, and now Ns is equal to mu change in velocity divided by m enthalpy change into isentropic. So now we can write down this equation again. Will velocity divided by V1 square divided by 2 into m V1 square by 2 divided by m change in enthalpy isentropic. Okay, now here I can write this thing is stage efficiency is equal to blade efficiency into nozzle efficiency. So this is coming from nozzle efficiency. Okay, optimum blade. Now we are going to optimum blade speed of a single stage turbine. ఓకే, ఒక సింగిల్ స్టేజ్ టర్బైన్లో మనకు వచ్చేసరికి ఏంటంటే ఆప్టిమల్ బ్లేడ్ స్పీడ్ ఎలా ఉంటుందనేది చూద్దాం. సో దట్ ఈజ్ ఈక్వల్ టు చేంజ్ ఇన్ roll velocity ఈజ్ ఈక్వల్ టు VR1 roll velocity cos beta 1 plus roll velocity cos beta 2. Then I can write this equation VR1 cos beta plus 1 plus VR square by VR2 by VR1 into cos beta 2 by cos beta 1. Now you can solve this. V1 cos alpha 1 minus u plus 1 plus kx. Now then here we should know about kx, where k is equal to Vr2 by Vr1, that is equal to friction coefficient. In problems we give friction coefficient, we can use this equation. Okay, and now constant c is equal to cos beta 2 divided by cos beta 1. Okay, now we know efficiency of blade is equal to 2u change wheel velocity divided by v1. Then we can write this u v1 into cos alpha 1 minus u by v1. Okay, 2u by v1 into cos alpha 1 into cos alpha 1 minus u by v1, and then it can go for density is equal to u by v1, that is equal to blade speed by fluid velocity of the blade inlet. Okay, that is equal to blade speed ratio. Okay, now efficiency of blade is maximum where differentiation of efficiency of blade by differentiation of rho, so that is equal to 0. Also d square efficiency of blade into rho minus 4 into 1 plus kx is the written for this equation. లేదా you can write dou by dou p into dou rho into 2 into cp cos alpha 1 minus p square. Okay, then here we put and 1 plus kx. Okay, this is equal to 0, or p is equal to cos alpha 1 by 2. Now here alpha is of the order of 18 degrees to 22 degrees. Okay, now then here rho pt is equal to v by u by v1 opt. So now that is equal to cos alpha 1 divided by 2. Okay, now for single stage impulse turbine. Okay, single stage impulse turbine. Now therefore the maximum value of blade efficiency that is called x is equal to written here 2 into p cos alpha 1 minus p square and then 1 plus kx. Now this is equal to cos square alpha 1 divided by to 1 plus kx. Okay, so and then now here we are going now I've written in here for equiangular blades. Okay, that is called here maximum is equal to cos square alpha divided by 2 into 1 plus k. Now if the friction over blade surface, example friction అనేది కనుక ఉందంటే, if the friction over blade surface is neglected. సో మనం ఇప్పుడు ఫ్రిక్షన్ అనేది కనుక నెగ్లెక్ట్ చేస్తే it will come from efficiency of blade maximum is equal to cos square alpha 1. So the fixed blades are used to guide the outlet steam or gas from the previous stage in such a manner so as to smooth entry at the next stage is ensured. Okay, now here I can write the fixed blades are used to guide the outlet, okay, steam or gas from the previous stage in such a manner so as to smooth entry at the next stage is ensured. Okay, and then k, the blade velocity coefficient may be different in each row of blades. Okay, so then work done is equal to u change in velocity plus change in velocity to exist. Now end thrust is equal to m vf1 plus change in vf2. Okay, now here the optimum velocity ratio will depend on number of stages and is given by, ఇక్కడ మనం గుర్తుపెట్టుకోవాల్సింది ఏంటంటే ఆప్టిమమ్ వెలాసిటీ రేషియో వచ్చేసరికి మనకి నెంబర్ ఆఫ్ స్టేజెస్ పైన డిపెండ్ అయి ఉంటాయి. సో దట్స్ ఫర్ ఆప్టిమమ్ ఈజ్ ఈక్వల్ టు కాస్ ఆల్ఫా 1/2n. ఓకే, now we are going to see here velocity diagram of the velocity compound turbine. Okay, compound turbine you can see here. Now first this is coming from first stage. So here is first stage. As usually we take from this is U. Okay, now this is U. Okay, and now here the velocity is going like this. This is coming from first stage. I put it here double one. This is here we join these two lines. This is the inlet real velocity. Can put here real velocity 1. So you can put first stage. This will come 1. And now draw the hidden lines horizontally and vertically. Now this is the point here we fix. Now this is coming from, flow velocity is there here, but in this we will discuss later. Now here we go to now about something in here. This is exist diagram. This is real velocity, we know very well. So 2 1 first stage. Simply this is coming from V2, 1 is first stage, and then now here this is velocity, flow velocity, we know very well. Okay, and now we take in here the flow velocity, real velocity, but this the entire of the coming from here real velocity will occur. This is for change in real velocity 1. Here we put it change in real velocity, that is coming from here change in real velocity. Okay, because of this is one of the stage. Now I am going to draw the next stage. Okay, so now here I fix the blade like this. This is coming from blade. Okay, so we are going to complete this one first. Now we know very well this is coming from alpha 2 and this is coming from alpha 1. So 1 is the first stage. Now this is angle beta, this is angle beta 1. So this is 1, this is 2, coming from stage first. You can write down like this. Okay, and now the flow velocity will come, this is occur here. You can draw the horizontal lines like this. Here also we put some horizontal lines. Okay, this is flow velocity and this is also flow velocity. Now this is coming from change in flow velocity. Change in flow velocity. Now this is the coming from exhaust thrust. Change in flow velocity is coming from like this. Okay, and then we go for second stage of this diagram, and what happened we will see. Okay, now similarly I take here is the point is called U. Okay, again I going to draw here second stage of the, what is this, second stage of the velocity, that's called from absolute flow velocity. Okay, now here I put V1, but this is coming from second stage. I put here 2. Look at this. In here This is also absolute flow velocity, but here is coming from first stage. I put it 1. Now we are going to draw the second stage of the turbine. Now here I put velocity, absolute velocity v1 and stage 2, like that. Okay, and now we know very well, join this 2. What it will come? Here it will come VR1, real velocity at 1, first inlet blade, and here we fix 2 means what is called second stage. Okay, and now then here also we are going to draw flow velocity. Okay, so this is the inlet. Now we are going to exit part, and here also same thing in exit part, triangle like this. This is coming from downwards always. We are 2 2. So exit part, outlet part, it will come represent 2. This 2 is coming from second stage. Exactly in here also V2 second stage. Now we are going to draw vertical line and horizontal line. Then here to here is representing, here to here representing change in real velocity 2. Okay, right. So now change in real velocity 2. Now we are going to fix in here. Similarly, we are going to draw the flow velocity lines. Okay, the horizontal. Look at this. I never change anything. So now this is the coming from change in flow velocity 2. Got it? Okay, and now we are going to fix the angles in here. This is, we know very well, 1 2. This is coming from angle, blade angle 2 2. Now this is coming from alpha 1, blade angle is coming from second stage, and now this is also coming 2 2 2. Okay, so this is the finally we got the stages. So this is called second stage. This is called second stage of the object. Okay, so this is the compound of the velocity diagrams. You can draw like this. Okay, now we are going to draw the problems in next class. Okay, thank you.